Good evening, Sunderland Astro. This is the beginning of everything. As you can see from the subtitle, I'm going to be describing the origin and the very early history of the universe. So we know the universe exists. How did it come about? When we look out into the universe, what do we see? Well, we don't see a uniform distribution of matter. This is not a simulation as such. This is more a 3D atlas. This is a map of lots of galaxies, 500,000 or a few million, that have been mapped out in terms of their position and their distance, and that has been used to reconstruct this 3D atlas that we're now flying through. So you can see that galaxies are pretty much everywhere, but not necessarily uniformly distributed. We see occasionally groups of galaxies, strings of galaxies, and occasionally some parts of space which appear to be rather bereft and rather sparsely populated with galaxies. So we know there's a lot of stuff out there. We know there's galaxies and stars and gas and dust. But where did all of this matter that we can see come from? In other words, what's the origin of everything we're currently looking at in this 3D map of our local universe? That's what we're going to be covering. We know that images like this one, a Hubble Deep Field, looking into the deep universe, we see lots of galaxies that are quite close to us and an enormous number of galaxies that are very remote from us. But we're looking this evening into the origin of these things. So I'm talking about the creation of the universe. When did it happen? Well, as far as we know, it happened 13.8 billion years ago. How long did it take to make the universe? Well, about 3 minutes, give or take. I'll explain why we come up with that number shortly. Where did it happen is often what people ask, and you have to remember that it happened everywhere. We're talking about the creation of everything, and therefore it didn't happen in one place and then drift out into the rest of space. As far as we can tell, space and time were born during the instant of the Big Bang, and it's been expanding ever since. Why did it evolve the way it did? Well, to the best of our understanding, it evolved the way it did because of the laws of physics. In other words, what I call the rules of the game. If we can understand the rules of the game, we can understand why the universe is behaving the way it is. How do we know all this? Same answer, because of the laws of physics. So I sometimes use this analogy of trying to work out what's going on in a game of chess. We're living in a universe, and we look out into the universe and we see stuff, we see matter, we see structure. If we were looking at this game of chess, could we work out what the rules of the game were? Could we work out how this particular collection of chess pieces ended up in this particular configuration? And the answer is, well, that's rather tricky, trying to work out what's going on. Perhaps we can work out that there's two slightly different coloured pieces, so we might guess this is a game between two people. But trying to work out the rules is rather tricky. Same thing if we look at a galaxy. We can't simply look at a galaxy, take a snapshot, and from that figure out how the universe came to be and how the universe has ended up looking like it is. A snapshot is simply not good enough. It would be great if we could simply watch this galaxy evolve, but that, of course, would take an awful long time. It would take hundreds of millions of years just to rotate once. Evolution will take billions of years. So it's the same problem with the chess game. Instead of having a snapshot, wouldn't it be great if we could have a movie of two people playing chess? Then we could figure out what the rules were. But we can't really do that with the universe. But we can do something almost as good. Instead of having a video of a chess game being played, what if we took a snapshot of 1 million games of chess, all at different points in their evolution? Same idea. Instead of taking a snapshot of one galaxy, if we can't take a video of it changing, what if we take a snapshot of thousands or millions or preferably billions of galaxies, all at different stages in their evolution? Then we might have a chance of figuring out what they're doing and what the rules of the game are that dictate how the universe ended up looking like this. That's effectively what a sort of deep field is doing. Whether it be the Hubble deep field or a James Webb deep field, they're both trying to get at the same thing. What's actually going on out there are early galaxies. Remember, the more distant galaxies, we're looking back in time because of the finite speed of light. And so a snapshot like this will include some local galaxies which are relatively close to us, and therefore we're seeing them as they are in the relatively recent history. But some of these galaxies are very remote, so we're seeing them as they were many billions of years ago. And if we take enough snapshots like this with enough galaxies, preferably millions if not more galaxies, then we stand a chance of working out what the rules of the game are. But you might say, how can we possibly work out the rules of the game for something so complex? Even if we just look at our local universe, here's just a picture of some gas clouds and stars that are relatively close to us compared to the more remote galaxies. Perhaps some of you recognise the Orion Nebula off to the top right and the Horsehead Nebula towards the bottom left. So this is a little snapshot of a part of Orion. But if you look at this, you might say, well, no, this is just way too complex. The rules that dictate how this came to be must be so complex we don't have a chance of understanding them. Well, let's have an analogy. Here's a mathematical analogy. Here's a complex set of coloured pixels. It's called the Mandelbrot set. It's a mathematically generated set of pixels, effectively. You're looking at, depending on the resolution of your TV screen or your projector, you're looking at maybe 1 million pixels. But the Mandelbrot set is much more complicated than that. This is just a tiny part of the Mandelbrot set. And if we zoomed in, we would see yet more structure. I'm not going to keep zooming in, but we can keep doing that effectively to infinity. It might look like the pattern is repeating. When we look at certain structures, we might see a structure that looks like it's repeating, but actually none of these repeat. They just look a little bit similar to each other. A bit like the fact that our Milky Way contains 100 billion stars. They're not identical, but some stars will be similar to other stars. So how complex is the mathematical formula that allows us to generate not millions, not billions, not trillions, but essentially an infinite collection of coloured pixels, of which we're looking at a tiny fraction here? How complex must that mathematical formula be that generates something as complex as this? Well, the answer is the formula that generated the entire Mandelbrot set is that. Z equals Z squared plus C. I'm not going to explain what Z and C are. The point is, it's a very simple formula. Using this formula, we can generate every pixel in the entire Mandelbrot set. So even though the Mandelbrot set is infinitely complex, the rules of the game that generated it are not. The rules of the game are straightforward and simple. One of my favourite quotes from Einstein was the fact that the most incomprehensible thing about the world, and for world you can take that to mean universe, the most incomprehensible thing about the universe is the fact that it is comprehensible. The universe doesn't owe us anything. We're just monkeys who came down from trees 500,000 years ago. Why should the universe be comprehensible to us? It looks like it is. If we study it and think about it, we can work out what the rules of the game are and understand why the universe has come to be the way it is. So what's the flow of thought that helps guide us in terms of figuring out what the universe is doing? Well, it started a long time ago, but to cut a long story short, we could say that a little less than 100 years ago, the observation was made that galaxies are moving away from each other. And we deduce that if galaxies are moving away from each other, if we have no special place in the universe, that must mean the universe is expanding. And we would get the same impression of what the universe is doing, regardless of where we actually were. So we live in an expanding universe. We can make experimental physics experiments. We can do experiments in the lab and we can draw conclusions from what we see. For instance, we can bang things together, we can produce particle accelerators like the Large Hadron Collider, we can smash atoms together and see what they're made of, and if they've got constituents we can bang them together and see what they're made of. So we understand the way the universe is put together at the fundamental level by doing physics experiments in the lab. We have to make some assumptions though. We have to assume that the laws of physics are immutable. In other words, the laws of physics for me are the same as the laws of physics for you, or the same as the laws of physics for somebody in Australia, or in the Andromeda Galaxy, or on the other side of the observable universe. If the laws of physics are different for everybody, then we can't make any progress in understanding why the world is the way it is. Similarly, we have to assume that the laws of physics do not change with time. In other words, the laws of physics today are the same as they were yesterday, and tomorrow the laws of physics will be the same. They're not going to change next year or in 10 years' time or a million years, and they haven't changed for millions of years or billions of years. Again, why do we make that assumption? Because if we assume that the laws of physics keep changing, then we have no chance whatsoever of understanding why the universe is the way it is. So we can't prove these two assumptions. That's why they're assumptions. But we can't make any progress without them. So we're assuming the laws of physics that we understand here and now are the same that have dictated how the universe evolved and how it will evolve in the future. So the conclusion we come to, observing the way the universe behaves and observing how things behave in the laboratory, we come to the conclusion that the universe must have been created in a very hot, dense state about 13.8 billion years ago, and it's been expanding and cooling ever since. So the big question, the one we're trying to address this evening, is where did all this matter come from? When we look into the universe, we see an awful lot of matter. We see galaxies and stars and dust and gas. Lots of atoms and occasionally particles that are not making up atoms. Where did all this stuff come from? How far back can we go in time before we have to say, well, we don't really understand what's going on. We don't know whether or not the laws of physics as we understand them today necessarily still hold. How far back in time can we go before we have to shrug our shoulders and say, we don't really know whether the laws of physics still apply? If the universe is 13.8 billion years old, can we go back to the first year of the 13.8 billion years and still say, yep, we're okay with that? Yes, indeed. First year, okay. First day. Okay, days didn't exist in the sense of Earth's rotation, but you know what I mean. Couldn't we go back to the first 24 hours of the universe and say, whatever the conditions were, we think we understand them? Yes. The first hour? Yes. The first minute? Yes. The first second? Yes. Can we go back to the first millisecond? Yes. First microsecond? Yes. First nanosecond? Yes. Can we go back to the first picosecond? Not really. At this point, there's a sort of a watershed. We can't really say with any honesty that we understand what happened prior to the first picosecond, the first trillionth of a second after the point of creation. We can't really say we know what was happening. We're on shaky ground. For reasons that I'll come back to in a few slides' time, we haven't any way of proving any hypothesis we care to make about what happened before 1 trillionth of a second, 1 picosecond. From that point onwards, we think we've got a story which seems to be fairly solid. In other words, we can verify any hypothesis we have based on experiments we can do in the laboratory. And therefore, if it's testable, we think the physics holds. So this talk, I've just given you a relatively long and somewhat rambling introduction as to what it is we're going to be dealing with this evening. I'm going to have one slide with a few basic ideas to make sure we're all on the same page before we start digging into the evolution of the universe from t=0 onwards. Some of those basic ideas I'm sure you're familiar with. Maybe some of them you're not. We'll then look at what happened in the first fraction of a second. We'll then look at the first few seconds, then the first few minutes. We're going to have to change gear somewhat, otherwise we'll be here until almost the end of time. We'll then jump forward the next 380 or so thousand years beyond that point. There's a reason for that number, again, which I'll come to when the time comes. And again, we'll change gear and fast forward 13.8 billion years to the present. So let's deal with a few basic ideas that we have to understand for the rest of this talk to make any sense. First idea, we are made of atoms. I hope that comes as no surprise to anybody in the audience. Atoms are essentially a positively charged nucleus surrounded by a whole load of negatively charged electrons buzzing around like bees. So atoms, given enough energy, can be split into their constituent parts of a positively charged nucleus and negatively charged electrons. So an atom is not fundamental, it's made of something else. Electrons are fundamental in the sense that they are particles, and to the best of our knowledge, they are not made of anything. They are just electrons. You can't take an electron, cut it in half, look inside and see what it's made of, because it isn't made of anything. Not true of a nucleus. A nucleus is a so-called compound particle. In other words, it's not fundamental, it's made of something else. Given enough energy, we can take a nucleus and break it down into its constituent parts. A nucleus is made of protons and neutrons. Protons and neutrons themselves are not fundamental. They are made of something else. I'm only going to consider the proton, but a proton can be thought of as three fundamental particles. They've got this rather silly name called quarks. We're not going to worry about why fundamental particles have ended up with the names that they have, but as best as we can tell, a quark is a fundamental particle that is not made of anything else. And a proton is made of three of these particles. And again, it takes energy to take a proton and attempt to separate it into its constituent parts. So as we go in terms of breaking atoms into their constituents, breaking a nucleus into its constituents, and so on, there's a sort of implicit energy scale here. It doesn't take much energy to break a molecule into atoms, but it takes more and more and more energy to break atoms or break a nucleus or break particles like a proton. And a physicist would say, well, low energy and high energy, that's sort of the same thing as low temperature and high temperature. Temperature is effectively just a measure of the average energy of particles in a collection of particles. So low energy and high energy are effectively low temperature and high temperature. But remember what we said about our conclusion of the universe expanding and cooling? If that's the case, then the universe started off hot and is cooling, so the time direction is as indicated by the right-hand side. The universe started hot and ended up cold, which means the universe was built from the bottom upwards. In other words, if you have a proton, you can't make protons and neutrons into a nucleus until the universe is cooled. Otherwise, there is so much energy around, so much high temperature, that the neutrons and protons would simply have so much energy, they would shake themselves apart and the nucleus wouldn't exist. Similarly, you can't have atoms in the early universe. You have to wait even longer until the universe is even colder before a nucleus and an electron can get together to make an atom. If you try and put them together any earlier, before the universe is cooled, then the nucleus and the electrons would have so much energy, an atom wouldn't be able to exist. So that's the idea of how things get put together, from hot to cold, from the bottom up. Quarks to protons to nuclei to atoms to molecules to us. So that's the basic idea that we're going to be looking at. So let's get the tricky one out of the way first. T equals 0. What happened at the instant of t equals 0? Time 0. Perhaps it's no surprise that when we try and answer the question, what happened at the instant of t equals 0, science cannot provide a definitive answer. Remember, we only really know what was going on from 1 picosecond onwards. So at t equals 0, the answer is we don't know. There's plenty of hypotheses as to what might have happened, but none of them are provable. And if they're not testable or provable, they will remain hypotheses. Maybe, people say, according to quantum theory, maybe there was such a thing as a quantum fluctuation, a jump in background of nothing, and that nothing changed in a quantum fluctuation. And this sounds rather weird, that we can borrow from nothing. If there's nothing there, how can we borrow? Well, yeah, it is weird. Quantum theory is weird. Quantum theory allows you to borrow energy from nothing. So if there was nothing there in the first place, it is possible, according to quantum theory, to borrow some energy and use that energy to make stuff, to make matter. Energy and matter are effectively interchangeable through E equals mc squared, the famous exchange rate, if you like, put forward by Einstein. So that sounds like a cop-out to say you can borrow energy from nothing. But, as I say, quantum mechanics or quantum theory is weird, and that's the subject of an entirely different talk. How big can this fluctuation be? In other words, how much energy can you borrow? Well, there is a limit, not to how much energy, there's a limit to the product of energy and time. In other words, you can borrow a lot of energy for a short time or a small amount of energy for a long time. That, again, is a fundamental limit set by quantum theory. Quantum theory's been around for 100 years, nothing yet has proved it wrong, so we have some confidence that quantum theory is telling us that is correct. So you could argue that what matters is how much energy do we have to borrow to make a universe? Well, how much energy is in the universe? If you add up all of the matter and all of the gravitational energy or the gravitational potential, all the matter is effectively a positive energy, all of the gravitational potential is effectively a negative energy. Add it all up, what do you get? Looks like the answer is 0. So if that's the case, how long have you got to pay back the loan of the borrowed energy? Well, if you're actually borrowing a total energy of 0, you've got as long as you like to pay it back. And I'm sure that sounds like a con. But then when you start looking at quantum theory, there's an awful lot of that. So the bottom line is we don't know. There are hypotheses, but we don't know. Let's move forward to something that we have some idea about. What happened after a time of 0.0000, you can count the zeros yourself, a very short length of time after t equals 0? Well, again, we're not yet at a picosecond, so we don't know, but it is hypothesized that at this particular point, the universe, the observable universe in which we live, was a lot smaller. Remember, the universe is expanding. At the moment, the observable universe, everything we can see, is inside a sphere of diameter about 100 billion light years. All of that used to be a lot closer together. At this point in time, all of that, everything in the observable universe that we see today, was only a few centimeters apart from each other. So it's difficult to believe just how dense such an object would be if you pack everything in 100 billion light years down to the size of a golf ball. Impossible to imagine doesn't mean it didn't actually happen. Just like a golf ball, I like this analogy because not only does it give you an idea how small the observable universe was back then, but the universe wasn't smooth. Just like a golf ball with dimples in it, the universe had dimples in it. Not dimples in the surface in the sense of a golf ball, but variations, small variations in density and pressure. It wasn't perfectly uniform because, generally speaking, quantum systems aren't perfectly uniform. Eventually, when this golf ball expanded until it was much, 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 much bigger, these small variations in density and temperature would have given rise to the variations in density that ultimately produce the large-scale structures in the universe. By large-scale structures, I mean the superclusters and clusters and galaxies that exist today that we see. So it's a hell of a stretch of the imagination from going something the size of a golf ball to going to something the size of our observable universe. Again, this is still the subject of a hypothesis. But now we're going to move on to what physicists would consider more solid ground. We're going to move forward to 1 picosecond, 1/1,000,000th of a second. The universe has expanded until it is now about the size of the solar system. Yes, of course, the solar system doesn't yet exist, but just to give you an idea of scale, we're talking about the golf ball sized universe expanding in a picosecond until it's many, many light hours in diameter. So clearly it's expanded much, much, much faster than the speed of light. Space can expand at any speed it wants to, so that's not violating any rules of physics. At this point, the temperature would have fallen to about 10 to the 15 Kelvin. And the energy of all the particles, whatever they are, having borrowed energy from nothing and used it to make particles, the energy of each of the constituents in this particular particle soup, I'm calling it quark soup. It will actually be a whole load of quarks, electrons, and probably other particles as well, but that's a bit of a mouthful, so let's just call it a quark soup. At 10 to the 15 Kelvin, the energy of each of the particles in the quark soup is, roughly speaking, equal to the energy of the particles that we can generate in the Large Hadron Collider. In other words, we can recreate the energies of the particles at 1 picosecond after the Big Bang. That condition can be replicated inside the Large Hadron Collider for particles smashing into each other. Therefore, if we've got any ideas about what we think happened at this point in time and this point onwards, it is possible for us to regenerate those sorts of energies and test out our ideas in a particle accelerator. And it's because we can test our ideas from this point onwards. Remember, the universe is cooling, so from 10 to the 15 Kelvin to cooler and cooler and cooler conditions, we can test in a particle accelerator, and that's why we think we have a reasonably good idea of what happened. Energy makes matter. Remember, E equals mc squared. Energy and matter are continually exchanging backwards and forwards. Energy can make matter, matter can make energy. Strictly speaking, it's not just matter, it's a combination of matter and antimatter. Antimatter is the sort of opposite of matter. Every particle that exists, like every electron, has an antiparticle. It looks like an electron, it has all the characteristics of an electron, but it has the opposite electric charge. A positively charged electron is the antimatter equivalent of an electron. And we assume that matter and antimatter were originally made in equal amounts, because that's what our understanding of the laws of physics tell us. When you have energy, you make matter and antimatter in equal amounts, and that matter and antimatter can then annihilate and make energy. Now, I don't know how to represent energy in a PowerPoint presentation, so I'm just going to put a big E, meaning energy. Energy can make matter and antimatter. Now, it'll probably make quarks and antiquarks. It's unlikely to make a tangerine and an anti-tangerine, but the point is it doesn't actually matter, if you'll excuse the pun. Energy makes stuff and anti-stuff. It makes particles of matter and particles of antimatter. It doesn't really matter what it makes, whether it's a quark and an antiquark, whether it's an electron and an anti-electron. Those matter and antimatter particles will be generated, and then they will annihilate, and that annihilation will produce energy again. And that energy would then be available to make another particle of matter and antimatter. Not necessarily the same ones again. This time it can make something different. Probably not a hot dog and an anti-hot dog, that's unlikely. It's probably going to make another quark or another electron or some other exotic particle. It will generate something and it's anti-something, and they will be continually energy to matter to energy to matter to energy to matter, back and forth, an awful lot. In this very early period of the universe, something odd happened that we don't really understand. Somehow, matter gained a very small excess over antimatter. Although we think they should be made in equal amounts, somewhere along the line on this sort of timescale, matter gained an excess over antimatter. In other words, lots of matter was made and lots of antimatter was made, but not quite the same amount of each. I've shown the excess here as being about 10%. It wasn't that big. The excess of matter over antimatter wasn't 1 part in 10, it was more like 1 part in a billion. So when the matter and antimatter annihilate to produce energy, and that energy is often in the form of electromagnetic radiation, perhaps originally gamma rays, now more likely to be lower energy radiation floating around the universe. Notice that the matter at the end there hasn't got a particle of antimatter to annihilate with, and therefore it survives. So we end up in a universe which is full of electromagnetic radiation, energy in the form of light, and we have a tiny bit of matter left over. That tiny bit of matter, that 1 in a billion excess, it's just as well there was an excess, because that is everything that we can see. That is every galaxy, every star, every mote of dust, every atom of gas. That is you and me and everything else in the universe that we would call matter. That tiny excess of 1 part in a billion. So it's just as well matter did gain an excess, otherwise we wouldn't be having this talk. Let's move forward to 1 millisecond after time t equals 0. Matter and antimatter are continuing to pop into and out of existence, back and forth and back and forth. Protons and neutrons are names that we give to constituent quarks that are continually transforming back and forth into each other. In other words, quarks are fundamental particles which were made, as far as we can tell, at t equals 0. And if we have 3 quarks, I'm not going to explain why we have U and D symbols. I'm not going to explain why the 3 constituents are coloured red, green and blue. But if we ever end up with 3 quarks in that particular pattern on the left, we call that particular bag of quarks a proton. That's just the name we give to this combination of quarks. And a slightly different combination of quarks, the ones on the right, we give that particular bag of quarks a different name. We call that a neutron. And given that quarks will be going backwards and forwards because matter is converting to energy and energy into matter, that means protons are changing into neutrons and neutrons are changing into protons, back and forth and back and forth. That will continue for quite a while. Let's move forward to 1 second after t equals 0. The universe has now cooled down to about 1 billion Kelvin. It is now too cold for protons and neutrons to readily change backwards and forwards. Remember the basic idea we started with? There's a whole energy scale, and once the universe is too cold, it is effectively impossible for the protons and neutrons to change into each other. Providing we have plenty of energy, they can go back and forth and back and forth. But once the universe has cooled, it's now very difficult for protons to change into neutrons and neutrons to change into protons. Now, protons, as it happens, are a little bit lighter than neutrons. In this particular talk, I'm labelling protons as little red spheres and neutrons as little blue spheres. Protons are a little bit lighter than neutrons, by only 0.1%, but it's a rather important difference. How do we know protons are lighter than neutrons? Well, because we can measure them in the laboratory today. And remember the assumptions, the laws of physics now are the same as laws of physics 13.8 billion years ago. So if protons are currently lighter than neutrons, they always were and they always will be, because they are made of fundamental particles called quarks. And it's only 1 part in 1,000, but it is important. Because protons are lighter than neutrons, protons and neutrons are not made in the same numbers. For every, I've taken an example here of for every 16 particles that are made, by particle I mean a proton or a neutron, notice that 12 of them are protons and only 4 of them are neutrons. They're made in the ratio of 75 to 25. Why does the universe make more protons than neutrons? Well, because nature always favours the lower energy, which, because of the equivalence of energy in mass, that means nature always favours the lower mass. Another way of thinking about it is, if nature is expected to make lots of protons and lots of neutrons, if the protons are lighter, it's easier to make than the neutrons. And 1 in 1,000, it turns out, when you work out the physics, if they're lighter by 1 part in 1,000 or thereabouts, we would expect the universe to make 75% protons and 25% neutrons if the temperature was about 1 billion Kelvin. What happens next? We're now going to go to the next 2 or 3 minutes. We're going to go to a time period of order 100 seconds or so, 100 to 200 seconds. Neutrons are unstable, and some of them decay into protons. Because they're heavier, they can change into the lighter protons. How do we know neutrons are unstable? How do we know they change into protons? Because they do today. In the laboratory, if you take a neutron and separate it from all its mates in a nucleus, after a quarter of an hour or so, a neutron will change into a proton. The laws of physics are the same now as they were 13.8 billion years ago, so we can calculate that some of those neutrons are unstable and will decay into protons, and that changes the ratio slightly. Instead of 12 and 4, the ratio of protons is now 14 to 2 in this little collection of 16 protons and neutrons that we were using as an example. So in other words, 2 of the blues have changed into reds. So now we have 14 reds and 2 blues, 14 protons and 2 neutrons. After 2 to 3 minutes, the universe has cooled to the point where it's now only 100 million Kelvin or so. That might still sound ridiculously hot, but remember, that's not necessarily much hotter than the core of a star. So it's a sensible sort of temperature. If the universe is 100 million Kelvin, nuclei can now form. In other words, these protons and neutrons can now get together. Remember, until this point, the universe was too hot. If you try and get neutrons and protons together while the universe is still hot, they have so much energy they just tear themselves apart. But now the universe has cooled enough to the point where neutrons and protons can get together. 2 protons are not going to get together because they're both positively charged, and as we know, like charges repel. They do now, they did 13.8 billion years ago. So 2 protons can't get together. But a proton and a neutron can. They want to get together, and they will get together and form the most stable structure they can. And the most stable structure that protons and neutrons can make is this one. 2 protons and 2 neutrons. It's called an alpha particle, or alternatively, the nucleus of a helium atom. So when we get 2 protons and 2 neutrons together, we're left with 12 bachelors. Notice that, of course, because protons outnumber neutrons, if 2 protons and 2 neutrons get together to form the nucleus of a helium atom, there's no more neutrons left for the remaining 12 hydrogen nuclei, or protons, because we can label them as protons or we can label them as the nuclei of hydrogen atoms, as we wish. So once that marriage has taken place and we've generated a whole load of helium nuclei, no more protons to make more helium nuclei, the rest of the bachelors remain hydrogen. So at this point, once all of this pairing has taken place, after about 3 minutes or so, at this point, the relative abundance of hydrogen and helium is fixed. The universe can't change it. Okay, it can make stars and it can start fusing hydrogen into helium, but that's a tiny variation on top of this fundamental ratio between 3/4 of the universe being hydrogen and 1/4 of the universe being helium. So notwithstanding the fact that stars will start changing that ratio ever so slightly, we can look out into the universe and look at all of the gas that's out there, and we can ask the question, in general, what's the universe made of? And the answer is, as indicated by this Big Bang Theory, we see that the universe is made of 3/4 hydrogen, 1/4 helium. This is one of the key reasons why we have faith in the theory that we call Big Bang Theory, because Big Bang Theory predicts that the universe ought to be 3/4 hydrogen, 1/4 helium, and it is. One of the basic tenets of Big Bang Theory, that's why we think it's right. We're now going to change gear and move forward 380,000 years, because nothing much interesting happens for the next 1/3 of a million years. The universe continues to expand, the universe continues to cool. It's still made of 3/4 hydrogen, 1/4 helium. Eventually, the universe cools to a temperature of around 3000 Kelvin, and it does that at this particular point, 380,000 years. Why is this temperature important? This temperature is important because at this temperature, it is possible for the nucleus of an atom, whether it be hydrogen or whether it be helium, it's possible for the nucleus to hang on to the electrons. Before this point, the universe was simply too hot, and any attempt for positively charged nuclei and negatively charged electrons to get together to make atoms, the universe was too hot and the atoms would have ripped themselves apart. But now the universe is cold enough for atoms to exist. So at this point, 380,000 years is the first point in the history of the universe where atoms exist. The universe changes from an ionized plasma, a simple collection of positively and negatively charged particles. It now changes into a gas made of atoms. For the first time in the history of the universe becomes transparent, because the gas is effectively transparent, whereas a plasma isn't. A plasma will continually scatter any light that's trying to escape. So light that up to this point was trapped inside the plasma is now free to fly through the universe. And that light can indeed be seen. The light originally at 3000 Kelvin, you would expect the light to be essentially white light. It will be visible light, perhaps some infrared, perhaps some ultraviolet. But at this sort of temperature, if you heat a block of anything up to 3000 Kelvin, it will radiate in the visible part of the spectrum. So its original wavelength was about a micron or so in the visible part of the spectrum. But the universe has expanded a lot since this time. The universe is now 1,000 times bigger. If the universe is 1,000 times bigger, that light, which originally had a wavelength of a micron, that light has now been stretched 1,000-fold, and that light is no longer a micron in wavelength, it's 1,000 times longer. It's millimeter. It's microwaves. And it's the microwave background of the universe which is the second pillar of the Big Bang Theory. Big Bang Theory says if the universe was this hot, it should have produced a microwave background. And the discovery of the microwave background was effectively the proof that Big Bang Theory is correct, or as close as any theory can be proved correct. So this is the entire sky unwrapped into an ellipse, and the radiation is coming from all directions because remember the Big Bang happened everywhere. But it's not perfectly uniform. Remember the golf ball sized universe had dimples in it, and those dimples led to variations in density and temperature, and that's precisely what we're seeing when we look at the cosmic microwave background. We're seeing small variations. I haven't put a scale on here, but these red blotches and blue blotches are not as dramatic as they look. They're only a few parts in a million of the background. In other words, there is a variation. There is a variation in fluctuations in density and temperature. They are not large, but they are measurable, and they correspond to the dimples in the golf ball 380,000 years earlier. And it's simply because that those variations, those fluctuations can be seen in the cosmic microwave background. Those fluctuations tell us about the fluctuations that existed in the early universe. So although they are tiny, only parts per million or hundreds of parts per million. Studying those is very important to help us understand what was going on in that very early universe. And more satellites will be built to study the cosmic ray background in more detail to help us understand and help us pin down the parameters that existed for that early universe. We've been doing that for decades. I'm sure we'll be doing it for decades to come, because you can't underestimate the value of studying the cosmic microwave background for giving us hard data about Big Bang theory. So the dimples in the golf ball gave rise to the cosmic microwave background. Essentially, those small variations in density and temperature collapsed over billions of years to give us the cosmic web of filaments and voids that give us the galaxies that we see today. We can run simulations to make sure this makes sense. This is a simulation. The link is at the bottom there. This is the TNG project, where they've taken a large cube of matter, small variations. Perhaps you can just about see that this blue has a little bit of mottling in it because it's not all the same density, not all the same temperature. You let gravity do its stuff over billions of years, and what do you see? You see the density varying. You see some parts becoming more dense and some parts becoming less dense. And you end up with a structure in the universe which is not uniform, but you end up with a web-like structure with lots of these white blobs are galaxies and clusters of galaxies and superclusters of galaxies. Some of them, you notice, are strung out in filaments. Some of these filaments connect to each other, and there are some areas which appear to be underrepresented by galaxies, these so-called voids, where there appear to be very few galaxies existing. This is pretty much what we see. Remember the survey, the 3D atlas that I showed you right at the start of the talk? That's pretty much the structure of the universe that we see today. So we can understand that by assuming that there were variations in the original cosmic golf ball and then letting gravity do its stuff and increasing the density to the point where stars and galaxies form at certain points within this cosmic web structure. If we look out into our local area, this is a sort of an indication of what our immediate neighborhood looks like. There's the Milky Way galaxy in the center, a few satellite galaxies. There's the Andromeda galaxy on the right and the Triangulum galaxy down the bottom there. So we're only looking a few million light years in terms of our neighborhood, and we don't see much other than the local group. If we expand the scale and go further, so the local group is now in the center, we start to see structures of, for instance, the Virgo cluster and other clusters like the Eridanus cluster, the Fornax cluster. Notice that they don't uniformly fill space around us. There are clusters, and those clusters appear to be grouped together on a filament. Remember the filaments of the cosmic web. This is what we see when we start looking on larger scales. If we expand the scale again and ask ourselves what things look like, well, it tends to look a little more uniform in that there are clusters of galaxies in all directions. But notice that, for instance, there are still on this scale some areas which appear to be devoid of galaxies, like the Boutets void on the right-hand side here. These clustering of galaxies and superclusters of galaxies and the Capricornus void and the Boutets void and the Sculptor void, these are all consequences of the dimples in the golf ball once gravity takes effect, increasing the density in some regions and decreasing the density in other regions. You could argue it's a natural consequence of what happens when gravity takes hold of something that is not perfectly uniform. So thanks to computer simulations, we've got a much better idea of how that happens. So we can go forward to the present day, jump forward 13.8 billion years. If it only takes 3 minutes to make all of the hydrogen in the universe, and then stars will use that hydrogen to start fusing hydrogen into helium and helium into carbon and nitrogen and oxygen and calcium and phosphorus and all the other elements that we understand. Along the way, those stars will make light and will radiate, so we'll have the possibility of life. But if it only takes 3 minutes to make all the hydrogen, you could argue, if you just take the big picture, Once we understand where the hydrogen comes from, then we understand the existence of galaxies and of stars and of planets and trees and mountains and snowflakes and rainbows and cats and... Okay, maybe not cats. I don't think we'll ever understand cats, but we understand pretty much everything else. That's a very broad statement to make. There's lots of detail that we still need to pin down. But essentially, if Big Bang Theory gives us hydrogen in large quantities, then we can sort of understand how the rest of the universe ends up looking like it does. Yes, there are details of cosmic evolution which we need to work out, and there are various details which we haven't pinned down yet. So let's think about the timeline. This is a ridiculous scale for the timeline. Very short time on the left, very long times on the right. And there's where we are now, 13.8 billion years. So in graphical summary, we don't know how everything started, but we think back at 10 to the minus 35 seconds, the observable universe, everything that's currently in the observable universe was only a few centimeters apart. That expanded and we ended up with quark soup, the energy and the matter continually turning backwards and forwards. Quark soup, remember, is not just these fundamental particles which we call quarks. It will also include electrons and various other exotic particles as well. But if we move forward to a timescale of seconds, these quarks eventually got together in batches of 3, which we either call protons or we call neutrons. If we move forward to hundreds of seconds, then these protons and neutrons get together to form either helium, if they can capture 2 neutrons, or any protons that are left are just what we label hydrogen. If we move forward to 1/3 of a million years, those nuclei, the hydrogen protons or the helium alpha particles, 2 neutrons, 2 protons, they will eventually capture electrons because the universe will be cold enough after 1/3 of a million years. And that's when the light is released. That light gets stretched from visible light to the microwave background that we see today. It would have then taken quite a while for stars to form. And that's one of the big questions. What happened after the production of the microwaves, but before the first stars and galaxies were formed? We don't know if that took a few 100 million years or longer. And that's precisely why telescopes and spacecraft, like the James Webb Space Telescope, for instance, are looking back in time to try and figure out when were the first stars born. If we know all of that hydrogen came into existence in 3 minutes, how long did it take to make the first stars? At the moment, it seems like it took a few 100 million years, but the theorists are still trying to work out how you can make a galaxy on that sort of timescale. So we know the galaxies exist now. We think the galaxies have been around for many billions of years, but pinning down the birth of the first galaxies is still a work in progress. And there still are some problems. There are still gaps in our knowledge. The jigsaw that I've been describing is not complete. I mentioned one fundamental issue. Why did matter win over antimatter? Why didn't the universe make the same amount of both? What caused the asymmetry? We know the asymmetry exists. If we look at matter and antimatter today, we can make antimatter in the laboratory. That's not a big deal. And we know there is an asymmetry, but what caused the asymmetry in the first place? We can characterize it, but we don't understand why it came about in the first place. And I've been talking about when we look into the universe, we see galaxies, we see stars, we see dust, we see gas. But what about other stuff? What about dark matter? It seems to be out there and it's causing galaxies to rotate at the speed that we wouldn't expect based on all of the matter that we can see. The visible, the luminous matter doesn't seem to account correctly for the rotation rate of galaxies. And don't get me started on dark energy. We don't know what that is and we don't know why it seems to be causing the universe to accelerate its expansion. The universe has been expanding for 13.8 billion years. It started off fast, then it slowed down a bit, and now it's accelerating again. Why is it doing that? This talk is entitled The Beginning of Everything, but I've been very careful to talk about everything, meaning all the matter we can see, all of the galaxies, all of the stars, all of the gas, all of the dust, all of the luminous matter that we can see. But that so-called everything isn't everything. It's only 4% of the total that's out there. The other 96%, the dark matter and the dark energy, is still a bit of a mystery. But, as they say, that's another story. Thank you for listening.